Great. OK, so yeah, serverless data pipelines at scale using AWS. So just a few words about me. So I'm a data engineer at GumGum, so building pipelines to get reporting for internal teams and as well external customers. I started data engineering a few years ago, so it was about writing like Java. My previous job was not very efficient, but that was fun. Yeah, we moved on a little bit. In my previous job, I had to do this as well, but on big mutualized hot-on-word cluster. But I didn't really like it because coming from AWS, it was feeling inefficient, like upgrading a cluster would require a battle plan. So I'm very happy to be back fully on the cloud now and using like new services to build these kind of pipelines. So we're going to, I just want to start with like the classic data pipelines just to be able to compare and to explain why we also need something a little bit different. I'm going to introduce you to the services we're going to use to build this serverless architecture. And then I want to talk about the tuning part and mainly about the limitations of these services and of the architecture. So at least you know what you sign up for if you want to go that way. So I've been building this pipeline at GumGum, and what we do is computer vision. And we apply this to different verticals, but the first one and the main one is advertising. And when we started, we came with this in-image format where we would detect what is in the image, and then we can apply it an ad to match the context, basically. And today, we use the same tech on two other verticals. On sports, we apply it on sports broadcast, on social media posts to capture the value of the sponsorships. And a very new project now is dental, same technology, but this time on dental X-rays images to detect pathologies from the images, so we can support the patient and the dentist. But I'm mainly going to talk about advertising pipeline because it's the main source of data for us, and especially about real-time bidding pipeline because that's the big one where we get the most data from. So yeah, classic data pipeline. I'm just talking about the classic like ETL pipelines. You're getting the data from somewhere. That's the extract part. Then you transform it. Maybe you clean it. Maybe you're filtering it. You're enriching it, depending on your use case. So that's the transform part. And then you load the result in whatever database you have. In the industry, it's common to differentiate the batch pipelines. So you like process files from the streaming pipelines. You just process the events as they come and store the results as they come. They both have different use cases. They work great. The tools you're using doesn't really matter. You could use maybe Kinesis instead of Kafka, maybe Flink instead of Spark, maybe other kind of databases. That doesn't really matter. Or BI tool, the architecture stays the same. But there's still something that is sometimes frustrating about these pipelines, and is, first of all, your data model is going to change because business changes, so you need to adapt your model to the new, like you need new fields. You need reporting on your data. And every time new fields are coming from upstream, you need to update the jobs to process these new fields. So that requires work from your team, your data engineering team, to update the Spark jobs and to update the schemas of your tables. So what if we could do that in a generic way? And the second point is it's so much data that you can't store everything on your data warehouse because it's going to cost too much. So sometimes we do like filter out fields, and we have like a period of retention for our Redshift database before deleting the rows. But sometimes we still need reporting of this data that we don't have in data warehouses, so we need to write custom Spark job to get the reports we need, and that's quite time-consuming. So again, if we can have SQL directly on the oh, that's back. If we can have SQL directly on the whole data set, that would be great, because no more custom Spark job to write, just SQL. So just to make it clear, when I say serverless data pipeline, I'm not talking about Lambda, because if I say serverless, you're thinking about Lambda. That's normal. That was the first serverless service announced here from Werner Vogel in 2014, already 5 years. That's crazy. But what I mean is fully managed services, because now the term changed a little bit. We can apply it to, I mean, Amazon does that as well, called serverless Aurora, for example. It's not Lambda, it's just fully managed. But it could be a legit question, like what if we want to replace our processing block with Lambda, but at our scale, it would just cost too much, because for this RTB pipeline, we have about 1 trillion events a month. And if we just start a Lambda for all the events, even though we have the smallest Lambda memory and very fast processing, that would be more than 200K a month, so that's impossible. So I'm not talking about that, just fully managed services. And just to make it clear very quickly, when I say fully managed, I mean so you don't run the software, you don't have to patch it, but also the instance is abstracted from you. I don't consider RDS, EMR, or Redshift being fully managed because, yes, of course, you don't install the software, but you still see the instances. You need to check if they're healthy. You need to maybe scale, or I need more instances. So I'm talking about the last block, like SaaS services, basically. OK, so what services are we going to use? First one. Most of you, I think, probably know about it. S3, that's the most common one. We usually start with that. So it's just the storage piece. Just keep in mind that it's not a file system. It's an object store. So it's a little bit different. You don't have hierarchies, folders. But also, you don't have all the POSIX operations. So you don't have a rename. It would be a copy and a delete. So if your Spark job writes a temporary file, a temporary output file, and just rename it, that's going to be costly because that's not a file system. But we'll get back to that. So the main service I want to talk about today, and that makes the big difference, is Glue. I don't know how many of you use it, but it's a very broad service. It has many pieces in it. And it's branded as a fully managed ETL. But I'm not going to talk at all about the ETL part, but only about the data catalog one, because that's the one I'm mostly interested in. And mainly, so first of all, it's a managed catalog, meaning it's going to store all your table schemas, and it's going to version them. So that's good. You don't need to do that yourself. But mainly, for me, the killer feature is the crawler. So you're going to set up a crawler to run against an S3 path. And depending on the content on the files that are stored on this path, it's going to create a table, if not created already, or it's going to update the table schema if there are new files with an updated version of the schema. And obviously, if the schema didn't change, but there are new files, not going to update the schema. And also, it's going to add the new partitions. You know, all these things we used to do manually. Oh, I have new partitions, so you have all the commands to do it. The crawler does that for you. So that's a very new kind of service. I don't know any other service that does that as well. And that's going to let us design the pipelines in a generic way, meaning I'm not going to create manually and declare the schemas of my tables, but Glue can do it for me. There are limitations, of course, we're going to talk about that. But if I can design my pipeline in a generic way, I have way less maintenance afterwards. So the last block we need is SQL on these files stored on S3. So we have two candidates here, Athena and Spectrum. So both of them are SQL and S3 files. Both of them are connected to the Glue catalog, so that's great. You don't need to do anything. You already have the tables declared there. I would just say if you already have Redshift data warehouse, go with Spectrum or with both. If you don't have a Redshift, go with Athena because Spectrum requires a Redshift cluster. So here we go. We have the full architecture, and it's actually quite simple. You store the files on S3. You have the crawlers that are going to crawl the files, update the table schemas here, and then you just fire Athena or Spectrum and create the files directly. I just want to talk briefly about the data format because I said files on S3, but what kind of files? It could be JSON, Avro, CSV. But it's great if you can have column-oriented formats. And the two famous and supported ones are Parquet and Orc. And it's going to be important in terms of performance and cost, because most of the time in your reporting queries, you're just creating like a few fields of your table. So let's say you have a table with 20 fields, but you're creating 2 of them. Then your query is going to be about 10 times faster and 10 times more cost effective as well, because Athena and Spectrum are built per how much data you scan. So, and just I'm going to mention Avro as well. So it's another kind of data format. This time it's not column-oriented, but it's binary. And if you use Kafka, you probably heard about it because it's quite common to use it. But how do we get these Parquet files? Because if you have like from upstream, I don't know, files like Avro files, for example. So a good candidate here is Spark Job. It's because it gives you API to quite easily convert the files to Parquet. So here is a quick example. And what's good is if you already have structured data like Avro files, then you don't even need to update those jobs while the schema changes, because you just call for the Avro schema, and then you load this Avro file and write it as Parquet. So like there is nothing dependent on the schema in your job. And even more, so this was like what data format, but even more important than that is partitioning, because you don't want to scan the whole files every time you do a query on these tables. And if you use like a regular database, most of the time it's being taken care of for you. Let's say you use Redshift. When you create a table, you declare a distribution key, and then Redshift does that for you. It's going to partition your table. Here it's different. You're the one in charge, so you need to build the S3 path in a way that Glue can detect as a partition key. So historically, we had this kind of formatting like 2019/03/27/16, but that doesn't work. That's not compatible with Glue. So we updated to this one. So you just need a partition key and partition value. Glue documentation like shows this kind of example, but I don't really like it because then when you write your queries, you have to, in your where clause, you have to declare all the partition keys, so that's quite long to do. Other example, just like mention DT equals, but just think about your end users because that's going to be the field they are going to use to filter on the daytime. So just make it explicit and maybe one partition key is enough. If you remember this query, so that's what we did here. We have the partition key. We can even apply ranges on that. So it's very important because that's basically how much data you're going to read. And if your query is just like about this time range, just use these files. So here we see one table and all the partitions in the Glue service. OK, yeah. So the big question is always data model. I want to talk about a bit about schema evolution and schema complexity, because the big question is what schema evolution operation is supported without breaking the pipeline, because we just leave Glue do all the job, but we are limited in terms of what kind of schema update we can do. Can I just add a column at the end, delete a column, alter a column? And something to understand as well is the schema is defined in different places. First, in your files, like let's say you have Parquet files, it has a schema. Then in Glue, in the Glue catalog, the schema is defined. But then every partitions of the table has a schema as well. So somehow they need to align well enough so Athena or Spectrum don't panic at runtime. So that's why it's the big challenge here, the schema evolution. And one big differentiator is your schema nested or flattened? When I say nested or complex, I mean like, do you have structs in it? Do you have arrays? Do you have maps? If you have flattened schemas, it's going to be way easier to support schema evolution. And you could actually use the Spark job that converts the file to Parquet to flatten and to explode your schema. That's going to make your life easier down the line. But we'll get back about it. Yeah, so as I said, the schema is defined at different level. And you need to tune your crawler the right way so it helps the schema evolution. And there is this option, inherit from table. And what it does is every time the crawler runs, if the table schema is updated, then all the partitions inherit from this new schema. So at least all the partitions and the table have the same schema. So that helps in our experimentation. We just had way less errors with that option checked. And it's not by default, so that's why I'm mentioning it. So we also had quite an issue with the group crawler, which is like, because we have 20 terabytes of new data every day, it was more and more files to crawl. And the crawler was taking more and more time. And after a few months, it was taking more than an hour to complete. That was too long. Because it means like in a year, it would be like 24 hours, and the whole pipeline wouldn't make sense anymore. But we just used the exclude pattern trick to filter out all the files that have already been crawled. And the good thing is the partitions are going to stay in your table. They're not going to be removed, but at least the next time the crawler runs. So for example, here, we excluded all the 2018 files, or here, all the files from January or February. So next time it runs, it just have the March files. And the crawler runtime went down to maybe 10 minutes. So that's a good workaround until the Glue team just make it faster. OK, so my favorite part, all the limitations, because you'll have some. First of all, I said you could use Spectrum or Athena or both. Just know that there are differences. It's not the same engine behind the scene. It's not even the same teams in AWS. They quite compete with each other. And some things are supported in Athena, some are in Spectrum. I'm not going to list all the things because I don't know all of them. But just be aware of that and expect some difference of behaviors. For example, and quite big ones sometimes, for example, nested Avro is just not supported in Spectrum so far, might change. Or if you have like, nested tables, you can't do a select star in Spectrum. So that's another limitation you have to know. But the good thing is, with time, they support more and more features. And we saw the last month or the last year, they tend to converge. So hopefully, in the near future, there are not so many differences anymore. Yeah, so I talk about it's great to have Parquet files because query are way more efficient. And we have many other pipelines that still have this job to convert the files to Parquet. But for these specific pipelines, the RTB one, the big one, it's so much data that it was actually costing a bit of money because it was 20 terabytes of Avro files to convert to Parquet, so it's a bit of data, a lot of data to scan from S3. And also, just writing the output files took a while because of the rename thing I mentioned at the beginning. So it was about 8K a month, and we just paused the job for now, temporary, and we just like directly querying the Avro files from Athena. It works as well. So we kind of moved the complexity from pre-processing to query time. But because we don't have so many queries today, it works. But yeah, just keep in mind that it can be expensive, that step. It might have changed a little bit because the EMR team just released a new committer for this very specific use case, which is writing Parquet files to S3 from a Spark job. So they just released a proprietary committer that works on EMR for that. But we're also looking, because we're getting the files from Kafka Connect, and they might support writing directly the Parquet files, which would be great, because then we'll have the best of both worlds, basically. So we're keeping an eye on it as well. Yeah, just to go back about schema evolution support. So what always works is, so you have a flattened schema, and you just add new columns at the end. This is what we use for most of our serverless pipeline, which means from the same table, we can query the files with the old schema and the new schema, and it works fine. The tests I did with the column deletion were positive as well. It was working, but I didn't test it exhaustively, so I don't want to tell you that it's going to work all the time. I need to do a few more tests for that. But for nested complex schema, the situation is a bit more complex than that. And we kind of dodged the issue so far because, as I told you, we are using Avro files for RTB, which is our only nested schema so far. And Athena just happened to support this very specific use case. So it works for us, but just keep in mind that because adding a subfield in a nested schema is just not adding a column. It's going to alter an existing column. That's why it's so hard to update such a schema. So there's still a bit of work here, and if you can flatten the schema, go for it, because that's going to be simpler. Yes, so that's great. We're using fully managed services. We don't have to take care of scaling the infra, but actually, we just have this image of unlimited cloud. We're going to have all the Lambda functions of all the capacity, but obviously it's limited. And you may hit the capacity AWS is willing to dedicate to you, and this happened to us. So this is Athena queries. You probably don't see much from the back of the room, but we submitted a bunch of long-running queries, but some of them would just sit idle and waiting for some other queries to complete to actually start the job. So here, there is 0 kilobytes of data scans because they've been submitted, accepted, but Athena is just not really running them. So that might be an issue for peak usage. And this one is a bit more general, but I would call that the black box effect of managed services, because once again, it's great. You don't manage the services, but you can only see what they show you. And when you're writing your Spark job, if it fails, you're going to check the logs. You're going to fix your job, and you're good. But here it's a bit different because you're using Athena, maybe it has an internal error, but all you can do is open a support ticket and wait for it. Or maybe you're going to have a glue crawler bug. We had one, some files were not properly detected. And it had been fixed after 3 months, which is fine, but sometimes you miss a bit of visibility because most of the time the support is not going to give you an ETA on bug resolution or feature request. So you don't exactly know when it's going to be fixed, and that can be an issue. If you're lucky enough to have enterprise support and you miss visibility on a specific issue, we found that asking your technical account manager is a great way to get visibility. just a few words on cost. Mostly about Athena. It was my main concern because you're being charged per query, and there was no great way to limit the usage, like per user. So there was a bit of concerns, but Amazon just released the work groups feature that lets you have these knobs at the user level, how much resources you can use. So that's great. That was my main concern about cost, but I'm not going to talk much about it because I have no experience yet. But there's these features now. And what I like with this design is your pipeline is going to cost you, it's directly depending on how much data you have or how much data you're querying. You don't have like idle clusters or servers you're not using. Yeah, you pay for what you use, basically. I've been talking mainly about limitations, but there are quite good bits I wanted to mention. It works fine. We have several pipelines this way, even the big one that is being used currently. And it's not super expensive, as well as in engineering time, because we don't update the pipelines except if you're hitting an issue, but so far it has been quite good. If you limit quite heavily your schema evolution type, as we mentioned. And also to get back to the custom report, now you just have SQL to all of your data sets. I mean, we have SQL on all of that. So for all the data that are not on our regular Redshift, that's a very great way. And most of the time, actually, like we are not the one, the data engineering team, we're not the one making these queries, but the end users, like maybe the data analyst or other teams, as long as someone can speak SQL or just use a BI tool, you can have access to this data. So that's quite powerful. And that's about it.
Any questions?
Hiya. With the Parquet format, what size files did you output in the end? Because I know there's a recommendation on Athena that they should be like 128 meg.
128, sorry?
The Parquet file sizes, when you convert in from CSV or Avro, what size files, Parquet files, are you using? And have you done any tests whether it makes a performance difference when they're bigger or smaller?
So it does make a difference. I think Amazon has a good blog post about it. It depends on the pipeline, how much data we receive, but it's usually a few hundred megs or a few gigs.
Okay, thank you.
Any other questions?
Hello. Hi. Just a quick question. How do you deal with GDPR and data structures in all this setup? Because it's very performance and cost optimized, let's say, to store all the data in a date time format. But then you have some other issues coming with it. Do you have this concern, or?
So for us, it's mostly how long do we want to keep the data. And it's quite the same solution, actually, because with your regular database, you will have this policy. Like in Redshift, after this amount of days or month, I'm deleting the rows. So here, it's quite the same. And it's actually even easier because you can apply the policy life cycles on your buckets. So you could like delete your data over time to take care of these requirements. So that's how we do it.
Any other questions?
Slightly off topic, but what do you use to sort of configure all this?
So in a more general manner, we use Terraform heavily at GumGum. But for this specific use case, we started like building them a bit manually because it was still like experimenting phase. But as we are getting more productionizing it, and now it's supported in Terraform Glue. So we are talking about it now.
How big is your data team?
So we have different data teams, but the data engineering team, which I'm part of, it's five people.
Okay, thank you very much. Thank you to Nicolas.